So I am here to finish up this example that we started in class and a few other examples to help you with using Maclaurin series and being able to write, series of terms, actual Maclaurin series for other functions. So for this example, we had used Maclaurin series that's given to us to find the Maclaurin series for the following. And in each case, we're going to write down the terms of the series up to x to the fourth. Well, for this particular problem, that's what we're going to do. And so we were able to recognize before in class is that here we can see that this function is essentially the same. The only difference is that the x was replaced with a 2x. So this is pretty much composite functions. So essentially what we need to do is we need to replace the x with a 2x. So wherever we see an x in the Maclaurin series, we want to replace it with the 2x. So essentially what this becomes is the sum as k equals 0 to infinity of 2x raised to the k power. All right, we can simplify that just a little bit because remember, a power to a power, we would multiply. So technically this is 2 to the k power times x to the k power. From here, now that we have Maclaurin series for this function 1 over 1 minus 2x, we can write out the series up to x to the fourth. So that means that we're essentially going to plug in 0, we're going to plug in 1, we're going to plug in 2, and who knows however many more after that until we can get to the point that we have x to the fourth. So when we plug in 0 into that function 2 to the k, x to the k, we are going to get 2 to the 0 power, which is 1, x to the 0 power, which is 1, which essentially is 1. When we plug in 1 for k, we're going to get 2 to the first power, which is just 2, and x to the first power, which is just x. When we plug in 2 to the second power is 4, k to the second power is just x squared. And we're essentially going to need to keep going because we're looking for our series up to x to the fourth. So when we plug in k equals 3 and k equals 4, we are going to get 2 to the third, which is 8, x to the third, and then 16x to the fourth. And because this is a series, we want to make sure that we include the fact that this series does continue, but essentially what you see on the board is your series up to x to the fourth. Similarly, we're going to do this as well for sine 3x and sine x squared. We're going to use Maclaurin series for sine x. This is the summation notation for sine x. In our reference booklet, it actually gives us the series written out in each of the terms. But for this particular case, we are just going to find the Maclaurin series, period. So that means we just need to find the summation notation. Unlike in the last example where it's asking us to write down the terms up to x to the fourth, we're not actually writing out any of the terms. We're actually providing the sigma notation to represent the Maclaurin series. So these two are actually just a tad bit easier. We just need to recognize that, as we can see, we're replacing x with a 3x here. And then for the second example, we're replacing x with an x squared. So we are going to substitute in a 3x everywhere we see an x into the Maclaurin series for sine x, because we're trying to get sine of 3x. So that's going to be what you see on the board, what I'm writing. This doesn't change, but this part is now going to be 3x, and we're going to raise it to the 2k plus 1 power. Now, because this is a 2k plus 1 power, essentially, yes, we would apply the 2k plus 1 to the 3 and to the x, but this is the most simplified way to write it, and that would be our answer. For the second example, we have the sum from 0 to infinity. Again, all of this still stays the same. But we're going to replace x with an x squared, and we still are raising it to the 2k plus 1 power. Now we could actually simplify this a little bit more because essentially we have a power to a power. And remember, whenever we have a power to a power, we are going to multiply. So this is going to be the sum as from 0 to infinity of -1 to the k power all over 2k plus 1 factorial x to the 4th k plus 2. And that would be our most simplified Maclaurin series for sine of x squared. All right, now let's look at one that's a tad bit more involved. We are going to use the Maclaurin series expansion for e to the x to write down expansions for e to the 2x, e to the 4x, and e to the nx, where n is an element of positive integers. Okay, so in our reference booklet, we see e to the x Maclaurin series written out for us as 1 plus x squared over 2 factorial, so on and so forth. Okay, but since we are trying to use our Maclaurin series expansion for e to the x, we actually want a series notation with the sigma to represent this Maclaurin series. So if we do look at e to the x's series, we're going to try to figure out how we can write it in a more condensed format. So I went ahead and pasted it in so then that way we can have it, we can see it. And so now let's see if we can figure out a more condensed way to do this. Well, the denominators are looking in the factorial way of 0 factorial, 1 factorial, 2 factorial, 3 factorial, so on and so forth. So our denominator is going to be k factorial in the denominator. And then in the numerator, our numerators are staying as 1, our x's are increasing per the particular k value that we're at. So this would be k is equal to 0, this would be equal to 1, this would be equal to 2. So then we can represent this as x to the k power. So this would be the summation notation for, or the series notation for e to the x. So for us to write down the Maclaurin series for e to the 2x and the others, we are essentially doing similarly what we did in the other problems. We're replacing our x with 2x for the first one, 4x for the next one, and nx for the last one. So for part 1, the summation is going to be from 0 to infinity of 2x to the k power over k factorial, which of course can simplify down to be the sum from 0 to infinity of 2 to the k x to the k power all over k factorial. And so then essentially what that would be, if it were written with the series written out, it would just be 1 plus 2x plus 4x squared over 2 factorial plus 8x to the third over 3 factorial, and so on and so forth. Of course, we could say 2, 6, 24, and everything like that. I'm just going to leave it in that factorial notation. You could do either. It will still be considered correct. Now we're going to look at for e to the 4x. Similarly, we are going to replace x with a 4x to the k power over k factorial. As we know, that would technically be 4 to the k, x to the k. So I'm going to kind of leave out this step, and I'm just going to go ahead and write out the sum. So it's going to be 1, of course, because when we plug in 0, anything to 0 power is 1. 0 factorial is 1. Then when we plug in 1 for k, we're going to get 4x over 1, which is just 4x. And then when we plug in 2, we're going to get 16x squared all over 2 factorial, or you could just write 2. And then when we plug in 3, we're going to get 64x to the third plus 3 factorial, or you could say 6. And the series continues indefinitely after that. How many terms do you need to write down? Well, as was stated in the last video and in last class, you want to give a few terms to represent what the series essentially would be. And then for part 3, we're getting to one that's just more general, where n can be any positive integer. So it could be 8, it could be 27, so on and so forth. We are essentially writing a general formula because there is actually a part B, C, and D that we will tackle after we get through part A, and we're probably going to need this. So then this is going to be 1, as always, because again, anything to the 0 power is 1. The next term is going to be nx. The next term after that is going to be n squared x squared over 2 factorial, n to the third, x to the third, 3 factorial. And as we can see, that is the general pattern. We take whatever that coefficient is, we multiply by x for the first term. As you can see, 2x, 4x, so that means it would be nx. The next one is we had 4, we had 16. Essentially, it is that coefficient squared. Then it would have been times x squared over 2 factorial every time for each of the terms. So we're essentially just writing a general expansion for any e to whatever x. So how is that going to be helpful? Okay, well, let's take a look here. In part B, it says to use the Maclaurin series expansion for cosine x to find the first 2 non-zero terms of the Maclaurin series expansion cosine e to the x. Okay, and then there's a part C in there as well. I'll probably do part C on another slide, but let's go ahead and tackle part B. So part B, cosine e to the x is what we're essentially trying to get, but we're going to use the Maclaurin series expansion for cosine x. Well, we know that cosine x from our reference booklet and also from the notes before is that it is the series 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th all over 6 factorial, and it keeps going in that respective pattern. So if I'm looking for cosine e to the x, that means I'm going to replace x in each one of these with e to the x, okay? It's that whole composite function. So it's still going to be 1. This is going to be e to the 2x over 2 factorial, because technically it would be e to the x squared. A power to a power ends up just being multiplied together. So that's how we get e to the 2x over 2 factorial. This one's going to be e to the 4x over 4 factorial, e to the 6x over 6 factorial, and the pattern continues, okay? Well, that e to the 2x and that e to the 4x, we found in part A that full expansion. So for us to be able to write, again, the first 2 non-zero terms of this expansion, we're going to essentially continue to expand this series with what we know or what we found from part A. So we know that e to the 2x was this entire expansion here in AI. Yes, we were able to simplify it down here, as we can see there. But I'm going to go ahead and write out part of the series, and you'll see why in a second. So this is going to be 1 over 2 factorial times the series for e to the 2x. We can rewrite e to the 4x over 4 factorial. That's 1 over 4 factorial times the series or the expansion for e to the 4x. And of course, we know this would continue on for e to the 6x, e to the 8x, e to the, you guessed it, the nx, okay? What was that, a triple I? Okay, but for the sake of the fact that when we write this in the like the actual sigma notation to represent the series, we use k. And so we're going to replace n with k. So how can I represent essentially the factorial that's happening in the front? Well, if we notice, each of the coefficients essentially are alternate between positive and negative. So we already know that we're going to have to take into account that it's alternating between positive and negative. And as we know, that's a -1 to a power. In the past, we would say it's the nth power, but remember, we're replacing n with k. And then how can we represent the factorial part? Well, it's 2 factorial, 4 factorial, 6 factorials, all of your even factorials. So then it's going to be 2 times k factorial, because that's how we're going to essentially get an even number each time. And then the series that goes beside it would be the one that we use to represent e to the nx. But remember, we're not using n, we're going to use k. And more specifically, actually, we're going to use 2k because that is the, essentially, it's going to be whatever the term is that goes into the factorial. That's what is getting plugged in for n. Because it's not every n value, it's every even one. So we're skipping. So we have to take that into account. So it's going to be 1 plus nx, or 2kx, plus n squared x squared over 2 factorial. But it's going to be 2k squared x squared 2 factorial, and so on and so forth. That, again, can be simplified down using our sigma notation. So then that is going to be 1 plus the sum of k equals 1 to infinity, -1 to the k power over 2k factorial plus the sum of k equals 1 to infinity of -1 to the k power times 2k over 2k factorial. All of this is going to be multiplied by x, and it keeps going after that. Now, if you're wondering, okay, well, why is it k equals 1 instead of k equals 0? Well, remember, k equals 0, no matter what our expansion was, what our series was, it always ended up being 1. Take a look. Right, our first term for every single one of these was 1, and that's when we started at 0. But since, I mean, we could essentially do the same thing here. Hold on, let me slide this down. We can do the same thing here, or we can leave it as 1, because to be honest, it really is going to, what we're really more concerned about here are each of these respective terms. And right now we're concentrating on that first term here, right? That first term here. How do we represent that in general? That is what you see here. When k is equal to 1, we're trying to alternate between positives and negatives, and we're trying to get essentially the sum of all of our factorials, factorial denominators. So that's going to be -1 to the k power over 2k, that quantity factorial. This next part right here is associated with the x. So we're trying to figure, okay, how can we get each one of these terms along with their respective factorials in the beginning? Well, that is going to, we need to represent the factorial that's in the front. So we still have that -1 to the k power over 2k factorial, but we need to essentially get every even number x value. And so that is our 2k that we see there. This can be simplified down, because if you think 2k factorial is essentially 2k times 2k minus 1 times 2k minus 2. So, and I'll write that out here in pink. And so on and so forth. So actually our 2k's will cancel out. And then our final answer that would represent the first two non-zero terms of the expansion are, there we go. 1 plus 1 is technically that 0 term, because when we plug k, that's when we plug 0 in for k, so that's not it. So now, so our first term is going to be the sum k equals 1 to infinity of negative 1 to the k power over 2k factorial. That represents our first term when k is equal to 1. And then to represent our second non-zero term, or when k is equal to 2, it's going to be the sum from 1 to infinity. Remember, not 0, because we've already taken care of that here. Negative 1 to the k power over 2k minus 1 factorial, because we canceled out our 2k's. And all that's going to be times x. It continues from there. So how can we show that for x near 0, cosine e to the x is approximately cosine of 1 minus cosine of 1 minus sine of 1 x. I'll do that on a new page, and I'll actually rewrite it so you guys don't have to keep flipping back and forth. Essentially, how is it those terms in the series for x is near 0? Well, if x is near 0, then that means that our higher order terms, you know, the terms that have your x squared, your x to the third, your x to the fourth, so on and so forth, into infinity, they're going to actually tend to get closer to 0. So therefore, since the further along the terms we get, it's getting closer and closer to 0, because remember, it's converging. That means that cosine e to the x is going to be approximately, using what we know from our previous part, 1 plus the sum from 1 to infinity of negative 1 to the k power over 2k factorial plus the sum from 1 to infinity, negative 1 to the k power over 2k minus 1 factorial x, and so on and so forth, what we proved from before. We're trying to show that cosine e to the 2x is approximately what cosine 1 minus sine of 1x would be. Well, let's take a look. Well, what is the cosine of 1? Well, the cosine of 1, using what we know about the cosine Maclaurin series expansion, which is this, we can say that, okay, well, cosine of 1 would be whatever we get when we plug 1 in for x. So that's going to be 1 minus 1/2, or 1 over 2 factorial, plus 1 over 24, or 4 factorial, minus 1 over 6 factorial, and so on and so forth. Okay. Now we also need sine of 1, which is this. Remember, both of these are from our reference booklet. So then that's going to be 1 minus 1 over 3 factorial plus 1 over 5 factorial minus 1 over 7 factorial plus, if you notice, it's essentially the missing pieces of each other. Cosine takes care of our evens, sine takes care of our odds. Now, what both of these can be simplified down to be is the sum from k equals 1, or sorry, 1 plus, because the 1's the same, so we'll just start from k equals 1. From 1 to infinity, our terms are alternating, so we know that's going to be negative 1 to the k power. and our denominator is essentially our evens factorial. To represent sine of 1, well, we know that it's essentially 1, okay, minus plus, my mistake, -1 to the k power over, this is our odd, so this one will be 2k minus 1. This is how we take into account that we are skipping over 2 and we're going straight to 3. Now, we actually need to adjust this, because if I were to plug in 1 here, this would give me 1 factorial. So this would essentially give me -1 over 1. And that is not going to give me that 1 over 3 factorial. So we essentially need to skip a term so that way we can get 1 over 3 factorial. So how do we take that into effect? Well, if we don't include the 1, and we actually start off with a negative sigma instead of a positive 1, when we plug in 0 for k, or sorry, when we plug in 1 for k, then that's going to give us a -1 over 1. So essentially give us -1, but if we make it a negative, that takes care of the positive 1. So then when we plug in 2 for k, now we're at 3 factorial. We're at a positive 1, but since it's a negative, it gives us that -1 over 3 factorial. So just tweaking the initial series, we're able to get the series that represents sine of x. And so as we can see, these terms right here, these Maclaurin series that represent sine of 1 and cosine of 1 actually are the exact same series that are in cosine of e to the x. So because of this, we are able to conclude, we're able to show, therefore, that cosine e to the x is approximately cosine of 1 minus sine of 1x. Using everything that we've done in parts A, B, C, and D, now we're going to find by direct calculation the Maclaurin polynomial of degree 2 of cosine e to the x. Well, the Maclaurin series for a particular polynomial degree was f of 0 plus f prime of 0x plus f double prime of 0 over 2 factorial, so on and so forth, which essentially ends up being the sum from 0 to infinity of f to the n power, or to the k power, 0x to the k power, I should think this one was k2, all over k factorial. Hold on, let me go back and look at the previous slides and confirm that. Yes, that is correct. So from, I want to say it was like from slide 5, you guys wrote down this formula. And so essentially this is what we're trying to find here. We're trying to find the Maclaurin polynomial of degree 2 of cosine e to the x. So in order for us to do this, we need to know what is our first derivative and our second derivative of our function. So our function is cosine e to the x. So then we need to find our first derivative and we need to find our second derivative. So that way we can find for a degree of 2. And then on top of that, we're going to need to find f of 0 once we actually find that. So to find the derivative, this is going to apply chain rule. We take the derivative of the outside, which is sine, negative sine with respect to inside e to the x. And then we multiply by the derivative of the inside, which is nothing but e to the x. So this becomes negative e to the x sine of e to the x. Now we need to do the second derivative. Well, the second derivative is a chain rule and a product rule. We take the first times the derivative of the second. The derivative of sine is cosine with respect to the inside. Then we multiply by the derivative of the inside. That's the chain rule. Plus the second times the derivative of the first, and the derivative is nothing but another negative e to the x. So this can essentially simplify down to be a negative e to the 2x, because I can multiply this e to the x and this e to the x. And this is going to be minus e to the x sine of e to the x. Now we don't necessarily have to simplify it, but we really just need it so then that way we can find f prime of 0 as well as f double prime of 0. And we actually also need f of 0. Well, we already know that that's going to be just cosine of 1 when I plug in 0. So that's going to be cosine of 1. When I plug 0 into the first derivative, that's going to give me negative 1 sine of 1. And then we plug in 0 into the second derivative, that's going to give me negative 1 cosine of 1 minus 1 sine of 1. Looks familiar, right? Of course it does. So then our second degree Maclaurin polynomial is going to be f of 0, which we know is cosine of 1, plus f prime of 0x, which is going to be a negative sine of 1x, plus our second derivative of 0, f double prime of 0 over 2 factorial, which we know is going to be a negative cosine 1 minus sine 1. Actually, it's going to be plus, we factor out that negative, all over 2 factorial with an x squared. Oops, I forgot it from the general formula. This is supposed to be an x squared because it ends up increasing. And that is our second degree polynomial of cosine e to the x.